Section: Introduction. In this section, we introduce Sketch of Thought, SOT, our framework designed to enhance reasoning efficiency in large language models, LLMs. We begin by discussing the background of LLMs and their role in reasoning tasks. LLMs are trained on extensive text data to predict the next word in a sequence. They perform well across various fields, but their efficiency is a concern since the costs rise with the number of tokens processed and generated. To utilize LLMs for reasoning, we employ prompts, carefully crafted instructions that guide the model's responses. We define a prompt template that includes task descriptions and examples. The reasoning process can be represented as the model generating a response based on the prompt and the query. One effective method for prompting is chain of thought, COT, which encourages models to break down problems into smaller steps before arriving at a final answer. However, while COT improves accuracy, it often leads to lengthy explanations that increase token usage and computational costs, particularly with larger models. Our goal with SOT is to streamline this process, reducing verbosity while maintaining or even enhancing reasoning capabilities. Section Summary. In this section, we introduce Sketch of Thought, SOT, a novel prompting framework designed to enhance reasoning efficiency in large language models by utilizing three cognitive science-based paradigms that reduce token usage while maintaining or improving accuracy. Our approach includes a lightweight router model that dynamically selects the most suitable reasoning strategy for each task, demonstrating significant reductions in token consumption across various reasoning datasets. Section: Sketch of Thought, SOT. In this section, we introduce Sketch of Thought, SOT, which addresses a major drawback of traditional reasoning methods: the excessive length of intermediate reasoning steps that lead to higher token usage and computational costs. Unlike previous approaches that mainly focus on shortening the input prompt, we aim to improve the reasoning process itself by changing how language models express their intermediate steps. We create specific prompt templates that help models generate more concise reasoning. These templates guide the models to produce shorter reasoning steps that still convey the same logical information, using fewer tokens. Our approach combines cognitive-inspired ideas with linguistic rules to control the structure and length of responses. We implement cognitive sketching by translating human cognitive shortcuts into systematic prompting strategies. SOT encourages language models to use efficient reasoning patterns, similar to how experts use shorthand in their fields. While our method can adapt to various reasoning paradigms based on cognitive science, we initially focus on three specific paradigms tailored for different reasoning tasks. Importantly, this implementation does not require fine-tuning the model, only well-designed prompt templates based on cognitive principles. Next, we detail these paradigms with examples that show how SOT simplifies essential reasoning steps into more efficient forms. 1. Conceptual chaining. This paradigm is based on how humans connect and retrieve related information. It creates concise logical sequences between key concepts, drawing from cognitive mechanisms that link information from different sources. For example, when asked about the currency of South Korea, we can directly respond with Korean won, using minimal text. This method is effective for common-sense reasoning and tasks that require establishing relationships between ideas. 2. Chunked symbolism. This paradigm organizes numerical and symbolic reasoning into compact steps, based on the theory that humans can only hold a limited number of items in working memory. We apply this by condensing mathematical reasoning into dense symbolic forms, allowing us to express complex ideas with fewer tokens. For instance, when calculating the final velocity of a car, we can succinctly state the result without lengthy explanations. This approach is particularly useful for mathematical problems and technical calculations. 3. Expert lexicons. Inspired by research on expert knowledge organization, this paradigm uses domain-specific shorthand to condense reasoning. Experts can communicate complex ideas efficiently using specialized terminology. For example, in a medical context, we can convey that aspirin is part of monotherapy with a simple response. This method is ideal for technical fields where domain expertise allows for significant information compression. Through these paradigms, we demonstrate how SOT can effectively distill reasoning into more efficient representations. Section Summary. In this section, we introduce Sketch of Thought, SOT, a method that reduces verbosity in reasoning processes by using specialized prompt templates to generate concise reasoning steps, thereby lowering token usage and computational costs. We explore three cognitive-inspired paradigms: conceptual chaining, chunked symbolism, and expert lexicons, that enable efficient reasoning across various tasks without requiring model fine-tuning. Section: Adaptive Paradigm Selection. In this section, we discuss our approach to selecting the most suitable reasoning paradigm for each query within the Sketch of Thought, SOT, framework. We introduce a lightweight router model that evaluates the characteristics of questions using linguistic cues like mathematical symbols, multi-hop dependencies, and specific terminology. This model helps us choose the best reasoning approach based on these features. We represent our router model as a function that takes a query and outputs one of the three reasoning paradigms, which are essential for efficient reasoning with large language models. The router is trained on examples paired with the appropriate paradigms, ensuring it operates with minimal computational cost while being adaptable to various input types. For our experiments, we evaluate SOT across 15 datasets divided into 6 reasoning categories, including mathematical, common sense, logical, multi-hop, scientific, causal, and medical reasoning. We also include datasets for multilingual and multimodal scenarios, using MMLU and its translation for multilingual tests, and the multimodal version of Science QA for multimodal tests. In terms of model configurations, we utilize the QWEN 2.5 models with different parameter sizes for our main and multilingual experiments. For the multimodal experiment, we use the QWEN-2.5-VL model, which can handle image inputs. To enhance efficiency, we implement flash attention 2 across all setups and maintain a temperature setting of 0.5 to balance reasoning consistency and diversity. For training our router model, we compiled a dataset of around 14,200 samples from our experimental datasets, labeling each with one of the three paradigms using a classification model based on Distill-BERT. This model processes only the question text, ensuring it can adapt to multimodal inputs. We trained it with a batch size of 64/5 epochs, using cross-entropy loss and a learning rate of 2E5. In our primary experiments, we assess the effectiveness of SOT, chain of thought, COT, and self-consistency across 15 English text-only datasets. We select 150 samples from each dataset's test split and follow a standardized evaluation protocol. For different question types, we measure accuracy by comparing model outputs to the correct answers. We also use GPT-4o for evaluating open-ended questions, as it handles edge cases better than traditional scoring methods. We track token usage during reasoning, excluding the final answer. For SOT and COT, we create exemplars to guide the reasoning process, and we apply self-consistency by generating multiple reasoning paths and using majority voting for final answers. The appropriate paradigm for each question is determined by our pre-trained Distill-BERT model. Section Summary. In this section, we propose a lightweight router model that selects the most suitable reasoning paradigm for each query based on linguistic features, ensuring efficient processing with minimal computational overhead. We also outline our experimental setup, which evaluates the effectiveness of our method across 15 datasets categorized by reasoning type, utilizing the QWEN 2.5 model family and a Distill-BERT classification model for paradigm selection. Section: Multilingual Experiment. In this section, we demonstrate the effectiveness of Sketch of Thought, SOT, in reducing reasoning tokens across different languages, specifically Korean, German, and Italian. These languages are compatible with our models and are part of the MMLU dataset, which has been professionally translated. While previous studies indicate that English often performs better than native languages in zero-shot chain of thought (COT) tasks, our focus here is on evaluating token reduction rather than just accuracy. For our experiments, we pair each non-English question with its English equivalent and apply our Distill-BERT model to the English version, ensuring consistent use of the selected paradigm across all languages. We also machine translate both the system prompts and examples into the target languages using GPT-4o. Since mathematical tasks usually yield less text with SOT, we concentrate on the management and astronomy domains from MMLU, which typically require more text-based responses. We select 100 samples from the test sets for each language domain combination. In our multimodal experiment, we show that SOT can also be applied to multimodal tasks, using the Quen 2.5-7 BVL model on the multimodal split of Science QA. We treat any images as context for the questions and exclude them from the paradigm selection process, similar to our unimodal approach. Overall, our results indicate that SOT achieves significant token reduction while maintaining accuracy comparable to COT across all model sizes. Specifically, we see reductions of 76.22%, 71.80%, and 71.90% for the 32B, 14B, and 7B models, respectively, with only slight accuracy differences. This efficiency gain suggests that extensive verbalization is not necessary for effective reasoning in language models, and the benefits of SOT are consistent across different model sizes, which is important for applications with limited computational resources. In mathematical tasks, we observe token reductions of 60.18%, 58.73%, and 59.44% for the 32B, 14B, and 7B models, while maintaining or improving accuracy. The chunked symbolism paradigm is particularly effective, allowing us to express complex calculations with minimal text. Notably, the 32B model shows improved accuracy, indicating that structured constraints may enhance mathematical reasoning by focusing on essential steps. For common sense and scientific reasoning, we see dramatic token reductions of 77 to 85% with minimal impact on accuracy. The 32B model even maintains a slight accuracy advantage in common sense reasoning while using significantly fewer tokens. This suggests that domains with established conceptual frameworks can benefit from concise terminology and structured representations. In logical reasoning tasks, we achieve substantial token reductions of 74 to 78%, with varying impacts on accuracy. Interestingly, multi-hop reasoning shows consistent accuracy improvements across all models despite token reductions, suggesting that limiting verbosity may enhance focus on critical connections. In the specialized medical domain, we observe significant token reductions of 57 to 78%, but with more variable accuracy trade-offs. This indicates that technical domains may require careful calibration of verbosity constraints, especially for larger models. Nonetheless, the efficiency gains remain substantial. Finally, our experiments show that SOT's advantages extend beyond English language reasoning to multilingual and multimodal contexts. In multimodal tasks, we achieve an 81.46% token reduction with a modest accuracy decrease. Similarly, in multilingual scenarios, we see consistent token reductions across Korean, Italian, and German, with minimal accuracy impacts. These findings suggest that SOT captures essential reasoning aspects that are applicable across different languages and modalities. Section Summary. In this section, we demonstrate that the sketch of thought, SOT, approach effectively reduces reasoning tokens across multiple languages and multimodal tasks while maintaining comparable accuracy to traditional methods. Our experiments reveal significant token reductions in various reasoning domains, including multilingual scenarios, up to 85.71% reduction, and multimodal tasks, 81.46% reduction, highlighting SOT's efficiency and applicability across different contexts. Section: Self-Consistency Improvements. In this section, we explore the improvements brought by self-consistency, SC, in both chain of thought, COT, and sketch of thought, SOT, methods, highlighting the balance between efficiency and accuracy. We find that while SC enhances accuracy for both methods, it significantly boosts the token efficiency of SOT. Specifically, the combination of SC and SOT achieves similar accuracy to SC and COT but uses 76.22%, 71.80%, and 71.90% fewer tokens for the 32B, 14B, and 7B models, respectively. This is important as it shows that SOT can work well with other reasoning techniques. The substantial token savings from SC, which involves multiple reasoning paths, makes SOT particularly useful in scenarios where computational efficiency is crucial. From a practical standpoint, the consistent token reductions we observe with SOT can lead to significant computational savings, potentially cutting inference costs by 70 to 80% in reasoning-heavy applications. This efficiency could enhance the use of advanced reasoning in environments with limited resources, like mobile devices and edge computing. Additionally, the minimal accuracy trade-offs across various reasoning tasks indicate that SOT is a true advancement in reasoning efficiency rather than just a compromise on performance. By organizing reasoning according to cognitive principles, SOT helps models concentrate on key logical connections and avoid unnecessary details, leading to more efficient reasoning without losing effectiveness. We also note that large language models have shown impressive reasoning abilities, largely due to prompting techniques that guide their thought processes. COT prompting was a key development, encouraging models to break down complex problems into smaller reasoning steps before arriving at final answers. This approach has inspired various extensions, such as self-consistency, which generates multiple reasoning paths to find the most consistent answer, and tree of thoughts, which explores branching reasoning pathways. Other innovations, like Coconut, shift reasoning into a continuous space rather than relying on discrete tokens, addressing different aspects of reasoning than our focus on token efficiency. In our pursuit of efficient prompting techniques, we have seen various strategies aimed at making prompting more computationally efficient without sacrificing performance. For instance, LLM Lingua compresses prompts to speed up inference, while automated prompt optimization refines prompts for better results. COT Influx uses a method to maximize effective COT examples, enhancing mathematical reasoning without needing to fine-tune the model. Other research has focused on efficient few-shot learning, showing how smaller models can be tailored for multi-step reasoning tasks. On the output side, techniques have been introduced to create more compact context representations, and a mixture of thoughts approach has been proposed to balance cost and reasoning performance. Recently, a reinforcement learning method has been developed to train reasoning models that adjust their computational resources based on task complexity. However, these methods often concentrate on input compression or optimizing reasoning structure, rather than addressing the verbosity of model outputs during reasoning. We also recognize a growing body of work aimed at reducing output tokens during language model reasoning. Concise chain of thought initiated more compact reasoning chains by instructing models to limit response length, while Scott introduced a two-stage method that first generates detailed reasoning and then condenses it. Building on these ideas, recent works have made strides, such as Constrained COT, which promotes conciseness through explicit prompting and proposes metrics for evaluating correct conciseness. Our approach seeks to overcome existing limitations by developing reasoning paradigms based on cognitive science principles, tailored to specific tasks for more effective token-efficient reasoning. While we acknowledge the significant benefits of sketch of thought for reasoning efficiency, we also recognize some limitations in our current approach. Although we dynamically select reasoning paradigms, we rely on static examples within each paradigm instead of adapting them for specific tasks, like arithmetic versus physics. Our evaluation is limited to models from the QWEN 2.5 family, which ensures consistency but raises questions about performance across different architectures. Additionally, the larger accuracy drops in specialized areas, such as medical reasoning, suggest that verbosity constraints may need domain-specific adjustments. Future work could address these limitations by implementing retrieval-augmented generation to enable dynamic selection of reasoning paradigms and task-specific examples. Developing more specialized paradigms could also help address cognitive operations not well served by current methods. Finally, training a reasoning model specifically on SOT could lead to significant advancements, potentially helping models internalize concise reasoning principles while avoiding accuracy penalties in specialized domains. More sophisticated paradigm selection models could incorporate additional signals beyond just the question text to enhance paradigm matching.